peaks are very narrow and well separated. However, if you measure in normal temperature and pressure, in normal air, you might have this kind of spectrum. So, sample thickness, it's very important. So, I have measured several years ago, we tested what's the effect of sample thickness. And the sample was natural uranium. So, it's this spectrum here. This is uranium-238, 235, this small peak here, 234, this peak here. And the thicker the sample, the poor resolution you will obtain. So, if you want to analyze, for example, this kind of spectrum, it's quite difficult, especially nuclide identification. However, you can analyze, but it's a little bit difficult. About radiochemical sample processing. Now this is a very simplified picture because I'm a physicist. I don't understand chemistry very much. But this is the sample. It should be dissoluted by putting, for example, some acid there into a liquid form, for example, by using wet ashing. Then you can do, for example, electrodeposition to a source plate. I don't know, do you do this method here, but there are different systems. So, in this case, the alpha peak shape is determined mainly by the detector properties and, of course, the measurement geometry too. So, several radio element separation techniques exist. I will not consider them here. You will be do something in the laboratory session. I want to see that, what kind of things you are doing here. So, in some cases, for example, in a nuclear accident, it's better to have the spectrum very quickly, because if you have to do some decision regarding the doses to humans, then it's essential that we can do the measurements and obtain the results as soon as possible. So it is possible that you do not do any radio element separation. All radionuclides might be in the same sample. Fortunately, in alpha spectrometry, there are not many radionuclides to be analyzed. So perhaps 10 peaks or 20 peaks, something like that. In gamma spectrometry, there might be 200 peaks or 400 peaks in the worst case. All right. The problem in alpha spectrometry is that if the nuclides are long-lived, half-life is long, then you could have very long measurement time. So in these nuclide cases, perhaps mass spectrometry is better, but it depends on the activity of the sample. All right, so I showed you this previously, I think so. So the ideal spectrum could be like that. So alpha emissions have single individual energies. However, in reality, the detector properties and sample characteristics too, they influence so much that the peaks are not so sharp. All right, let's look at closer these peaks. Neptunium, polonium. Let's check this peak today. And this is 244. Curium. Several nuclides has only one alpha peak. Some nuclides has mainly two peaks. But there are nuclides like this Neptunium or americium, which emit several alphas of different energies. However, in some cases, simplified sample processing is possible. For example, in this case, if we have a water containing some radionuclides there, we can just evaporate the water and put that sample directly to the alpha chamber. We can have a spectrum like that. And it is possible to analyze that kind of spectrum. So this is a very simple method. I understand this. I don't understand chemical things, but I can understand this. But the analysis might be quite complex. So you need a specific software in these cases. I think this sample contained radon and its progeny. So there are 1, 2, 3, 4, 5, 6 nuclides in this spectrum. All right, let's go to the equipment. So these are alpha spectrometers that you have here in this laboratory. These are in some of, or has been in one of our moving cars. So more small NIM rack, vacuum pump and a computer. So there is a power supply, multi-channel analyzer here, and this is in fact the spectrometer. Here is the vacuum chamber. In our laboratory we have these kind of systems there. Perhaps you have seen alpha detectors, but they are in fact very, very small, and they are located at the top of the vacuum chamber. Canberra or present Mirion, they will sell this kind of equipment which measures air filters. You just put the filter here, piece of filter, close this tray, and you might get out this kind of spectrum. Well, resolution is not very good in this case, but no vacuum is needed here. In nuclear power plants, they have quite often these systems, continuous air monitors. Sampling is done here. This is the alarm system, and this is the spectrum that comes out from that system. Okay, let's go to detector properties. This is only a semantic view of a PIPS detector. This PIPS is a commercial name of Mirion. So it's a silicon detector. This is the active volume of the detector, which detects radiation thickness around 0.2 millimeters. However, there is a small dead layer in front of the detector. Its thickness is very, very small. However, in these kind of equipment, the dead layer might be much bigger, order of 1 micrometer or so, and it's composed of aluminum typically. There's backing, source backing plate, and the source is located here. So, let's talk about detector response. So, it is influenced by these things, how charge is collected from the detector, what's the thickness of the dead layer, the measurement geometry, in fact, source size and source to detector distance SDT. Alpha particle behavior in the detector material, and perhaps the presence of recoil ions or some contamination in the detector. So peak broadening is practically observed even in the case of monoenergetic alpha particles. However, there are some other relevant issues which might be in some cases important. For example, coincidence particles. You can see these also in alpha spectra, properties of the material, source material. And if there is some additional material between the detector and the source. Okay, let's look at the detail of the detector. I mean, very small part here. So this is like a zoom, this one. So this is detector material, 0.2 millimeters. This is the source. And this is the dead layer, very, very thin. So what's the effect of this dead layer? In case if you are measuring the source at large distances, in this case 3 centimeters, you can get a very narrow peak. And the reason is that practically all alphas go perpendicularly to the detector, to the sensitive layer of the detector here. However, if source to detector distance is only 0.5 centimeters, very close to the detector, then what happens? Some alphas go like this, but some alphas go like this. So they lose energy here. And this happens. So there is more tail. So if you have a high active source, and if you want to have very good energy resolution, then use larger distances. But the point, for example, I don't know how active is that polonium source, maybe very low active, then you have to measure it very close to the detector. I mentioned that there are other particles that detector may detect in addition to alphas, electrons perhaps, X-rays, photons, but they must be low energy photons because this is more thickness and gammas go through that detector without any interaction. So the effect might be this. This is americium-241. I will not explain this anymore. You can do homework later, but this is quite complicated issue. But my point is just to show that these electrons for low energy photons has a role too. And this effect is especially visible at small source to detector distances. About the backscattering. It's more like the same phenomenon than in gamma spectrometry. So it may happen that this alpha here goes at first down, then scatters up to here. So there is a big energy loss, and alpha energies may be here. Or it may happen that the alpha go like this, or like this, it scatters back. This is an example for polonium-240. So, the detector responds to monoenergetic alpha particles. It is assumed to be Gaussian. I mean this component here. However, there are sometimes like this very notable tail. So there are several response functions described in the scientific literature. So there might be 2 or 3 or even more components for the tailing. In this example, there are 2 components. I named this as a fast component. I mean that it goes fast down to 0. This goes down to 0 more slower. Okay, let's look at the influence of source properties. This is important. So if you have a thick source, it may totally destroy your spectrum. So the source characteristics has a major importance on the quality of the alpha spectra. I have an example here. Around 10 or 20 years ago, one USA professor contacted me, and he wanted me to analyze some very interesting samples. In fact, the samples were from Spain. Perhaps you have heard the case that a nuclear B-52 bomber, it's a very big airplane, dropped accidentally nuclear bombs in the sea coast, and one bomb goes to the ground. There was no detonation, but the bomb material dispersed on the ground. Okay, then I studied one of the samples, and this is an example of one nuclear bomb particle, diameter of around 25 micrometers. it mainly contained these two radionuclides. And this is certainly very thick source, even that you cannot see it in a naked eye. It's not possible because it's so small. So, as you can see, this is the spectrum that I got out. So what happens? Okay, this is a cylindrical source here, but it happens that very many alphas hit the sample itself and don't go to the detector, not at all. Okay, some alphas may go to the detector if they are located quite close to the surface. All right, then I would like to...
Here you have not prepared the source. You have kept the sample as it is?
No. I took a SEM picture. This is a SEM picture, this one. And then I isolated this particle from the sample. I wanted to investigate characteristics, it's a difficult word, characteristics of the particle properties. I'm not interested on the bulk material, because there is, of course, natural radionuclides, and I was not interested on natural nuclides in that case.
You kept the particle straight away, without any source sample preparation?
No radiochemical separation. So it was quite tedious process.
Okay.
I can explain that later.
Yeah, okay.
Okay, but let's go here. Now I will show you.
But what was the conclusion from the sample?
I will. Maybe some of you have installed this so-called ASI program, Advanced Alpha Spectrometric Simulation. And I will show you here just now. I will later present this much more. But let's take two short examples. If I click here, open, I will show what happens. So, some years ago, me and my colleagues made just a short test. We used a membrane filter, and we took a sample from outside air. So, air contains for example, polonium-214, 212, and bismuth-212. So these are normal nuclides, at least in Finland. I think that same thing holds also here. So this is part of the measured spectrum. Let's see one thing. I will change the axis. All right. You can see here is some other, not a peak, but almost like that. This comes from betas, low energy photons. Perhaps some detector noise too. Okay, simulation is very simple by using this ASI software. Just put one. So this is total simulated spectrum. So it fits very good, very good. in this case. I will show you details later. Let's look at another example. There is a Thule particle. I will explain this more. Oh, sorry. 0 to 6 MeV. So this is, I removed the text here, sorry. This was quite similar particle than the one I showed you. It contained also plutonium-241, 239, and americium-241. Same kind of spectrum. Is it possible to simulate like this one? The size was almost the same as the previous particle. I know the dimensions of this particle. I will explain this later, but the simulation is, in this case, very simple. Okay, I have to change the color. Let it be blue. Perfect. If you want to understand alpha spectrometry, I strongly advise you to use this software. You can download it from Stux PVV pages. I will give you the address. Please do that, because I have learned a lot on alpha spectrometry by using this software. And just before the laboratory session, I will more show you how this works. All right, let's close this program. Now, okay, I closed it. Stage 3 and alpha spectrometry and oh, I'm stupid. Let's do it this way. So, by using this ASIS software, I studied different effects. So, this is the effect of the particle size. Let's assume that I have two nuclides, these two ones. This is the case in which there is a point source. This is the case where the diameter of the point source is 1 micrometer, so very small. This is the case when the point source, I mean, this is a spherical point source, like a small particle. In this case, this is 5 micrometers. Do you have now any questions or comments? Please ask me.
What is the thickness of the point source?
I don't remember just now. Perhaps it was same thickness as the uranium, UO2 perhaps. Sorry. this is in fact particle size. So this point source is ideal point source. Dimensions are practically 0. This is a particle of diameter 1 micrometer, and this is diameter of 5 micrometers. So the influence is very big. Again, simulation, the effect of particle size. If you have this kind of particle, for example, located like this on the source plate, you may obtain this kind of spectrum. If the same particle is located like this, then it's the green one, 1 micrometer particle, the blue one. So even particle shape has an influence. What about size distribution? If you collect a sample from air, particles, radioactive particles has different size. So in this blue case, I assumed that all particles has a size of 1 micrometer, blue one, and in this case, red one, I assumed that particle size is log normal, which is typical in outside air, with mean diameter of 1 micrometer and standard deviation 2.
So the dB is 1 micrometer. That is
Yes.
monodisperse particle without any distribution.
Sorry,
Which you are telling.
dB
is 1 micrometer we are giving.
Yes.
A particle diameter. It is a monodispersed. Means all the particles are of same size.
Yeah. Yeah.
The other one is with respect if at all it has
There
some
is a particle distribution, size distribution. So the effect of filter type. If you take an air sample, you have to know what kind of filter material you are using in alpha spectrometry. So in these cases, you do not need to do any sample processing. Not at all. Just put the sample inside the vacuum chamber. That's it. So, in case of a membrane filter, the peaks may be quite sharp. And in case of glass fiber filter, not so sharp. Do you have any idea what's this? Why? Okay, membrane filters they are very thin. And practically all the particles stay quite close to the surface of the membrane filters. However, in glass fiber filters, the particles may go deeper into the filter. And that's why there is much more tail.
If you put the filter directly in the alpha spectrometer chamber,
Yeah,
because
directly.
of the vacuum,
Yeah,
will this particle splash over and contaminate the detector?
it is possible. I will explain soon.
Yeah.
Okay, let's look at the influence of the medium material. Okay, let's assume that this is the detector, this is the source. And let's assume that there is some material between the source and the detector. For example, a thin foil, very thin, to prevent recoil contamination, for example. Again, this is peak for polonium-200, 210. If you put a material between the detector and the sample, the effect is this. It may shift the peak location here. Why? Because there is energy loss here. It also has an influence on peak tailing. Number 2 here. Alphas go in different directions. And of course, rounding the peak top is also possible. So it's clear that this medium should be as thin as possible. Okay. So now I think that you understand much more this effect. Do you think, is this clear? All right. This is my last slide. Now regarding the question of Karunakara. So, in some cases, medium material might be important. For example, to prevent recoil contamination of the detector. I mean that if you put this source very close to the detector, you might have some problems. Because if alpha goes this way, the recoil nuclide, which might be radioactive, go this way and may go to the surface of the detector. And it's a problem. So it's better not to use absolute vacuum in the vacuum chamber. It's better to have a small amount of air in the vacuum chamber, just to prevent this recoil contamination. Even small amount of air is enough. Total vacuum is not good, even though the resolution is better. And of course, this contamination. If I put a filter without any manipulation, then I think it's better to use a thin foil here. So particles by mechanical particle detachment might cause the particles go to the detector. All right, this is my presentation. Avanias, please.
What kind of medium can we put between the detector and the source so that alpha can pass through but not the...
I have used 0.5 micrometer. It's a polyethylene.
Polyethylene.
Yeah. But they are quite expensive. The thinnest ones. They are expensive.
But they
Perhaps.
will have
Sorry? Alphas go through.
Okay.
Yeah. You can easily test it by using different layer thicknesses. It's easy to test.
We have a thin film of mylar.
Mylar is, yes, mylar is.
Film of mylar on
My-
the detector.
Yes, it's possible to put mylar here, for example, around the detector. Mylar is good. I think maximum could be, if you are using mylar, maximum thickness could be 5 micrometers or something like that. It depends, of course, on the alpha energy you are looking for.
Won't any medium attenuate the alpha particles?
Sorry?
If I put a medium between the alpha source and the detector, wouldn't it attenuate? Wouldn't there be a chance of attenuation of alpha particles?
Yes, it will attenuate, as I shown here. The effect is practically this one. I suggest you to test it, this phenomenon. And then do simulations many times and because using this ASI software, it's very easy. Any more questions? If not, I suggest to have a 10 minutes break. Is it possible?
Yes, yes,
So we will back at 11 o'clock.
yes. Yes.
Yes, please. Yeah. No, it's okay to. If you talk 1 hour, then it's.
I'll bring home for you.
All right. Do we wait somebody? What do you think? Okay, I can start. So I'm sorry about the delay. I had to do some administrative things, but let's start. So let's talk about calibrations of alpha and gamma spectrometers. So I firstly talk about alpha and then gamma ray spectrometry. So the main point is that if you want to obtain quantitative results, then you need to do good calibrations. Of course, good calibrations are not necessary if you report only some qualitative things. So, main calibrations, they are energy, resolution, and especially efficiency calibration. Energy calibration means that you are able to identify the radionuclide, which peak belongs to which nuclide. Very simple. Resolution means that you are able to calculate peak area correctly. And this refers also to efficiency calibration. So, as I showed before, this is the equation for calculating the activity. If I remember the paper that you gave yesterday in page 6, there is a, please look at the page 6 equation. Bottom part of the page 6, there's an equation how efficiency is calculated and so if you solve efficiency from this equation, it gives you efficiency is N over T I, which is the gamma or alpha yield, and A activity. So if you look at the equation, this N here in page 6, it refers to this, the count rate. This is count, and here it's a number of counts. Here is the time. And if they are divided, it's count rate. So the equation is basically the same. All right. So this N here refers to mainly resolution calibration. So you have to determine the area correctly. This energy calibration refers to this and this. I mean, you have to identify the nuclide I in question, and you have to find out data from the nuclide library. And of course, this refers to efficiency calibration. So, as I think Karunakara already said that energy and resolution calibration can usually be done only once, because they are more or less stable. However, the efficiency calibration is a little bit difficult because it depends on the source properties. So it has to be not necessarily calculated in each case, but it has to be taken into account correctly. I mean, you should have a correct reference material with same geometry. Okay, let's look at the energy calibration. So, it enables to identify radionuclide and in question. And I said to you, you can find the correct data from the nuclide library. In often cases, linear calibration is okay. Sometimes you have to use, for example, second order polynomial. But it depends on your detector and amplifier or electronic characteristics. Okay, there are of course some other functions that can be used, but linear is okay. But the resolution. So it's important for n. So peak width here is a peak. Width is usually characterized by using full width at half maximum. So this is the maximum of the peak. This is so-called baseline, and this is in the middle of the peak. So, and this is full width at 10th maximum here. This is not very often used. This is often used, this WHM. But there is strong energy dependency, especially in case of scintillation detectors. At higher energies, the resolution is much wider than at lower energies. The effect is more or less same in high resolution gamma spectrometry, but not so stressed effect. So peak shape, it is usually Gaussian. However, shape of X-ray peaks is Lorentzian. However, we do not consider these Lorentzian things because it's only for X-rays, and photon energies are quite low. In those cases, we are in this course analyzing or using only gammas. In alpha spectrometry, the shape is in fact same, the main shape. However, there is notable tailing. In this case, there are 3 tails. This one here, the tail number 1 goes rapidly down to the 0, T2 goes slower, and this tail, if it will be taken into account, it goes very slowly to 0. So there are, in fact, many different ways how to determine peak efficiency calibration. So one way is shown in this paper that Karunakara gave us, Karunakara and his team, but there are several others. Efficiencies can be calculated by Monte Carlo simulation. There are software for that, but in those cases you have to know detector characteristics very well. You have to know detector dimensions, detector to source distances, thickness of the dead layers, etc., etc. Especially dead layer thickness, it's quite difficult to get. But it has a very big effect in gamma spectrometry. You can use also numerical approaches using standard radionuclide sources like Karunakara's teams use, and it's possible to combine all of these. I do not mention here our way. We do it by using efficiency transfer software. So our basic calibration for one geometry is done by using this way, basically in the same way as you do. But for each sample to be measured, we are using this efficiency transfer method. So every time we calculate new energy calibration, if we want to analyze the spectrum of each sample, every time. Okay, let's look at the efficiency calibration in alpha spectrometry. There are also several ways to do that. One way is to use tracer material. The tracer used in the present measurement, was it polonium-209? Yes. So if you know the tracer material activity, then you can calculate very easily polonium-210. Okay. So the efficiency is entirely determined by the solid angle subtended by the source detector system. So this is the solid angle here. And our software, ASI software, that you will get it from Stuk. This software can calculate it very, very easy. I will show it later. So the assumption is that there is no big energy loss in the dead layer or in the source. So I mean that alphas are not stopped in the source field, for example. So in case of this calculation, you have to know only detector and source diameters, and of course source to detector distance, and that's it. It's easy to calculate, basically. Well, in mathematically it's not necessarily very easy, but by using our computer software, it's really easy. So you will get this material, of course, and you can download it from this link. Or use Google, and using words stuk and aasi, you can find it very easily. And this aasi software can determine the geometric detection efficiency. Perhaps I will check, I will close this now. Let's check that, is it still open? No. I will show how it goes. Like it's this screen here. So what's the typical source to detector distance in your measurement? Is it
1 centimeter.
1 centimeter? Let's put it here. 10. All right. So what's the diameter of the detector or area?
450 mm and
Is
650
it more or less same?
Yes, 450 mm.
Yeah. All right. What's the typical source diameter you have?
Diameter is 1 centimeter.
1 centimeter. Okay. Very easy. Okay. This offset means that it may be off the symmetry axis. Okay. Let's run the. So this is the efficiency. I think that you should test this software in your cases.
We have done the experiment and got the same value.
Yeah.
17%.
Yeah. All right.
Okay, this efficiency, it is simulating for, for an ideal case.
Yes,
But
ideal
if
case.
your sample, for example, plating is not clean, there is some deposition of, for example, iron,
Yeah.
and there will be self-attenuation.
Yeah.
How the software will account for that?
It assumes that there is no, how to say it in a very good way. It means that it assumes only that all alphas emitted from the source goes to the detector.
Okay. So it doesn't account for the imperfections in the source preparation.
Yeah, but the peak shape could be very wide also in those cases.
Yeah,
You just have to calculate all the counts.
Okay.
So this is only geometrical detection efficiency.
Okay.
I think that in your paper you call this as you call this as it was somewhere here mentioned, intrinsic something. No, I don't find it.
That efficient equation they are not given.
No. All right. But this is very simple. Let's close this one. where are we now? We are here. So please note that there are several analytical ways how to calculate this geometric efficiency, but I can guarantee that this is the most easiest way to do the calculation, definitely. And this is correct, this number that you get out. We have shown it in our scientific publications. All right. What's this slide? Sorry, I don't remember why I put this slide here. So one thing which is very important is that you have to, if there are quite short-lived nuclides, then you have to take into account the decay, so you have to determine correct reference time for the calculation. But this is the same equation as this one in principle. So I looked through one of the papers shown here. Letters are very small, but some scientists studied the effect of if we are using different vacuum chambers. There are small effects. Okay, in this case, uranium-233, the effect is, well, not very big. The numbers here are so small that I can't see very well, but this is the source to detector distance, this one.
Is he getting 60% efficiency? CPS per alpha percent, this graph on the y-axis?
It seems to be CPS per alphas per second. Yeah, I guess so.
That's quite large. 60% efficiency is quite large.
You can check these numbers by using this ASI software. And please read the paper also. Let's go to gamma ray spectrometry. So, same methods as mentioned in the previous slides can be used in this case. In the next slides, I will show you how we do the efficiency calibration. But basically, it's very simple. So you calculate the efficiency like this. You have to know the number of emitted gammas per unit time, which is reported in the source certificate. And number of detected gammas per unit time is obtained by the measurements. Of course, you have to apply appropriate corrections, for example, reference time correction, etc. But very simple, basically. But in fact, it's quite tedious work if you want to do comprehensive uncertainty calculation. Then it's a very big job. So, as an example, in our lab we have 18 detectors. And characteristics of the detectors are a little bit different. Most of them are broad energy germanium detectors. Some of them are coaxial. Some of them are appropriate for Marinelli beakers. There are also some special detectors, one weld type, one Compton suppression device, one alpha beta gamma coincidence system, one cosmic veto system also. We are measuring really several types of samples, any kind of samples, including individual particles. So how to do efficiency calibration in those cases, efficiency determination in those cases. So are you able in this laboratory measure samples with low amount of material? What about point sources?
Point sources will have high activity, but we are able to even detect samples as low as 5 grams.
Is this 5 grams minimum amount of material?
Not really. If I can put it in even a smaller beaker, and the activity is quite high, I think I should be able to detect it. But so far I have started from 5 grams. 5 grams of sample.
Yeah. All right. So, and my organization is responsible to do rapid measurements during an emergency. And this means that we have to do measurements quickly and do the analysis also very quickly. If the sources are high active sources, then we have to use larger distances. And we have very many different measurement geometries, or could have. These are the basic geometries we are using, so-called T beaker or Williams beaker. These are the volumes we can put into these beakers. So problem is that every case, in every type of sample, every amount of the sample, we have to determine new efficiency calibration. So in our case, it's just a mathematical way, so-called FTran software we are using. It's an efficiency transfer software. I will show its operation also later. I don't know, is it tomorrow or Friday or later, but let's see. So in our case, I have to think very carefully how to do with the efficiency calibration. Because we have so many detectors and so many geometries, and I think that we cannot operate like you are operating here. So, what's the starting point of the efficiency calibration? You must have certified sources. We have liquid sources produced by National Physical Laboratory from Great Britain. Your sources are, I guess, from IAEA. Yeah. These are the certificates. This NPL is a primary laboratory, so these sources are very well characterized. Typical uncertainties in each nuclide is of the order of 2-3%, something like that. So, by using these certified sources, our chemistry team made several calibration samples of different geometry, which gives us full traceability to the certified sources. So, as I explained to you, this is our basic calibration, so-called T20. This T20, this T means this T beaker, and 20 means 20 millimeter of liquid in this beaker. And if we are using this geometry, this V beaker, double V beaker, then we use efficiency transfer method. So only one calibration per detector. However, in case of Marinelli beakers, so the detector must fit here in this hole. We have 2 calibrations. But for the rest of the detectors, only one calibration. So if you're doing measurements from each calibration sample, basically you should do very many measurements and use different sources which are made in the same way as the first one. This is to check that the liquid that we made or put into this beaker, they are always the same. But we have 18 detectors, so it's not possible to measure, for example, 5 calibration samples per detector. So that's why we very carefully measured only once, so that we get very big peaks, lower limit 10,000 counts per peak. So statistical uncertainty is less than 1%. I mean square root of this number. In terms of percentages, of course. So, efficiency was determined for each detector with full and traceable uncertainty analysis. I will show it later. So, we also have a lot of different reference sources from which we know the activities very well. For example, filters, sources with different thicknesses or diameters, and we know the activities very well. Because we are using this FTRAN software, we have to do it this way just to verify that the basic calibration is okay, and also the efficiency transfer calculation is okay. And once we have shown that it is okay for the certified reference samples, then in normal samples we can rely on the calibration. Okay. This is an example of one calibration spectrum. So it starts with lead 210 in the very beginning of here and ends at yttrium 88 here. So the peaks are well distinguished. However, there are some minor problems, but they are quite small. So you have to remind that we also take these X-rays, which are located here. Energies are close to 10 kiloelectron-volt. We can take these into account in some of our detectors, not all. So, how it is done in practice? We have a Excel spreadsheet form which was made for each detector. One Excel for each detector. So, in our gamma team we have around 10 persons. And my policy is so that I said to them, I made, can I show it here? I made this Excel sheet so that those other persons, they should fill only things that are marked as red here. I will explain soon. All other numbers are made by me. The point is that every, at least high-level analyst should understand what does calibration mean. So it's not very evident always. All right, so it's like a training purpose. So the form includes full uncertainty estimation of the efficiencies. I will show this you, I guess, in Friday or Saturday. So the detectors are grouped according to their characteristics. This is because if we don't do this, the uncertainty calculation would be too tedious because of the large number of the detectors. So the measured raw activities that we get from the measurement, it's basically this one. It is fitted by using a log polynomial function. And lower energy is less than 120 kilo electron volts separately from higher ones. So this part is fitted separately from this part. Okay, and we validate calibrations by using different certified sources. Okay, let's look at the spreadsheet, but not very detailed way, because there are too many numbers here. So we used two sources, one with mixed nuclide source and one with only lead 210. This is for the mixed nuclide source, this part of the spreadsheet, and this part is for only lead 210. You cannot see the numbers here. You should check the PDF file, but these are nuclide names and their activities here. So what does the analyzer do? It just put peak areas and its uncertainties, and then this spreadsheet calculates the peak efficiency, which is located here in this part, and also this part for low energy gammas or X-rays. And you can see the uncertainties. In some cases, they are a little bit bigger, but in most of the cases, the measured uncertainties are quite small. So this is, so I call it raw efficiency, this curve here, because of this. So this part of the spreadsheet, the numbers are exactly the same as here, but I did fitting so that I can got a smooth curve. And then this part here is the uncertainty of the fit.
What kind of sample is this?
Sorry, what?
This material. Is it water, salt?
It's almost water. Little bit acid there. So how the fitting is done? It's in fact quite complex process. I will show it here. Sorry for you. I will. Okay. I will write down. So these are the measured points. Uncertainties are, in most cases, they are more or less the same in each case. Thanks. So how I did the fitting. So first I did the fitting using log polynomial function by using these reference values. So the curve is like that. Then I added these uncertainties to the measured points and made fitting using these values here or these values down. Like this. Because sometimes fitting process is quite mathematically difficult to do. So final efficiencies are here as a function of energy. In this case, starting from the energy of 6 keV and ending up to 3 MeV. Let's look at the data. This is the mixed source. So in the top part of each Excel, we have how to say it? We put there all basic information of each measurement. Who is doing the analysis, what's the dead time, how long does the measurement take, etc., etc. This is relevant basic data that must be taken into account. Then, according to the Nuclide-specific data and the reference material, this is the information from the certificate. It's this part for each nuclides. This part is number of counts of each peak and its area uncertainty. These are reported by the analysis program. We are not using GIAN in gamma ray spectrometry. We have a program of our own, so-called Unisampo Shaman. It's well, quite good program. Then there is a part of coincidence correction. It's a quite difficult area. I will neglect it here, but we took into account coincidence correction too for each nuclide. In some nuclides there is no coincidence correction. For example, in case of cesium-137, there are no corrections for that. And this part is quite interesting because one of my students, in fact, made this part in his Master of Science thesis. This is the uncertainties on the basis of measurement geometry and beaker. For example, beaker bottom thickness might vary. It is possible. Beaker diameter may vary, not much, but a little. All these things are taken into account in this area. And then we get the final raw efficiency as a function of energy or different nuclides. Then I explained how I made uncertainty fitting this way here. This is the upper limit information, lower limit information, and final efficiency. So you do not need to look through all these numbers. I just want to give you an idea how we did it. There are different ways. But I think that this is quite, at least from our point of view, it's quite good way and quite reliable way, because now there is a full uncertainty estimation, which is reliable. I think so. Because all relevant uncertainties are taken into account. So, how to validate the original efficiency calibration? Okay, as I explained, we use different reference sources. In this case, we use detector known as G5. It is just a name. All right. So we know the nuclides present in the reference source. We know the activities of the reference source here. And then we make a measurement for that reference source, put the activities here, and compare the results to the reference source. In this case, there are 3 different reference sources. So how we do, or how it looks like this efficiency calibration in our analysis program. So this is energy, I mean the horizontal axis, and this is efficiency here. So as you can see, we are not using smooth function. We are using interpolation between each determinate value. Are you using functions in your efficiency calibration? I mean that if some nuclide is in this area, around, let me say, 40 kiloelectronvolts, are you using function or a linear interpolation?
We use linear.
Linear, yeah. All right.
But the software has the option for both.
Yeah. Yeah.
It has an option called by dual efficiency, dual energy.
Yeah.
For the higher energy one side and
Yeah. So do you have any questions on gamma ray point? You can later check all these slides, and please contact me later if you want to know something. But that's our way. There are several other ways to do things.
So, in one of the graphs, efficiency graphs, you showed the peak curve and then a total curve.
Yeah.
So what is a total?
Total count, that one, yeah. Total count, total, so-called total efficiency. It takes into account, so the spectrum, it takes each count into account of the whole spectrum, and it is used for coincidence correction calculation.
It means it takes account of even.
It summarizes all the counts. So it's an integral. I don't explain it here because it's quite complicated issue with this coincidence correction. We have no time for that. So, okay. But,
I have a question.
yeah, of course. Please.
You are using multiple sources, right?
Multiple,
Sources.
yeah,
But the half-lives are different, right? So
Yeah.
some will decay faster.
yes,
So you need to
That-
change the sources.
Yes.
Regularly.
yes. In each case, we take reference time into account. So in each case, we calculate the activities to a certain reference time. It has to be done like that. How to explain? It is possible that some nuclides, short-lived nuclides, might die totally away from the sample. So then let's look at the example here. Is here any? Okay, for example, I think it's this sample here. I don't remember what is the sample for it, but for example, this cerium isotope tin, chrome, tin, strontium, they have decayed off. So we do not take into account in this test case. It's not a problem in this case. Okay, they have died and we just neglect them. But remember that this is not a efficiency, our basic efficiency calibration. This is only for checking that our so-called T20 calibration is correct, because this is our starting point, this T20 calibration. Just to check.
So originally, first time when you do, you use all the.
Sorry about the noise. Yeah.
Originally, when you do for the first time, so you use a high strength sources.
Did it got the point? Sorry.
So when you do it for the first time,
Yeah.
all these sources will be there in the sample.
In the first calibration sample, all the nuclides are there. However, these samples shown here, reference samples, they are perhaps, and they are indeed more old sample.
Okay.
They are just to check that the primary calibration is okay, and our efficiency transfer calculation is valid. Just checking. I hope that you understand the idea of this. It may sound quite a strange way to do things, but I can guarantee that in our case it's the best possible way to do the correct calibration, because of the great number of gamma ray spectrometers. All right, let's look at the role of low energy alphas or gammas. So, let's look at first alphas. This is part lower energy part of a gamma spectrum, alpha spectrum here. So this is for americium-241 and very thick sample, 0.1 millimeter thick. Okay, it's in terms of alpha spectrometry, it's thick, but of course it's very thin. So here are signals from electrons, betas, and electronic noise. How to calculate peak area in this case? Any idea? Well, this is not an easy issue. However, it can be taken into account in this by using this ASI software. But we do not, in fact, know basically how many counts are, in fact, here, which are below the energy of 0. I mean, which are totally absorbed, because the sample is so thick. So the answer is, I think that there is no easy answers. You just have to calculate how many alphas are totally absorbed. But this is an extreme case, this 100 micrometer thick source. In case of gamma spectrometry, this is okay. This is part of our calibration measurement. So we have nuclide, lead, americium, cadmium, and a lot of X-rays here. So basically, we cannot do the spectrum analysis here because this is too complex area, and this rest part of the spectrum, there is dozen of radionuclides. So you are starting your analysis up from 30 kiloelectron volts. Yeah. Yeah. So if you have only 1 or 2 nuclides in your radionuclides in your sample, then you might use that part into account in the analysis. But normally there are many, many of them. And for example, in the case of electron capture decay, the X-rays may be in true coincidence with gammas, which might cause additional peaks in the right side of the gamma peaks. However, in the efficiency calibration, we used only lead 210 liquid in the basic efficiency calibration. So this is 46 kiloelectron volts, and these are the X-ray peaks. Now, in this case, when there is only 1 nuclide, we can take these peak areas into account in the efficiency calibration. Like this. I look at the data from nuclide library. I put some peaks together, like, for example, this peak number 1, it's located here. It consists or contains 2 X-rays. This peak number 2 contains 1, 2, 3, 4, 5, 6, or 7 sub-peaks, if you call it like that. And in this item 3, there are 4 peaks. I fitted the areas using our analysis software, and then I calculated the efficiencies here. So note here, 10 kiloelectron volt is the lowest energy in practice. But normally we do the analysis as same as you do above 30 kiloelectron volts. These are used only for the coincidence calculation. Okay, is it? No. Okay, this is it. I'm sorry that this presentation might be too difficult and complicated. So you have to know the basis if you understand everything. But this is advanced alpha and gamma spectrometry course, so I had to put these things here. All right, do you have any comments? Was it too heavy for you gone above here? All right, no questions. What's the time now?
It's 12.
12. So what's the lunch time?
1.
1 o'clock.
Yeah, or maybe 12:30 if it is early.
Yeah. Okay, so we have a small break, and I will show how this ASIS software can be used.
Okay.
So let's have a 10 minutes break. We will go back here exactly 12:20. Yeah. Is it okay? Thanks. Shall we start now? Okay. So I will here show how this so-called ASI program functions. I show you some slides about the operation principle. Then we can do some simulations. But we have to define source types, define what is the material between the source and the detector. I neglect coincidences in this case and how to calculate geometrical detection efficiency. So this is for alpha spectrometry. And especially intended to those cases in which alpha measurements are easy. Easy in the same way as you are doing gamma ray spectrometry. Just put the sample, for example, in the vacuum chamber, measure it and analyze it. No chemical, radiochemical processing. All right. So, advanced alpha spectrometric simulation. I thought that sometimes Finnish persons have a strange level of humor. So what does this ASI mean in Finnish? It means donkey. We are crazy sometimes. Okay, so this code is intended to investigate source properties that influence the shape of the alpha peaks. And sometimes this is very useful when you want to understand, for example, those hot particles that I showed you. You can characterize source properties. Just doing a spectrum measurement and then try to do some simulations. So you can calculate easily geometrical detection efficiency in different measurement geometries. You can easily generate synthetic alpha spectra, and this is the main thing. When you are doing the simulations, which are very easy to do, it's a good way to train or to understand what's happening in alpha spectrometry. And once more, the code takes into account the properties of the detector and various characteristics of the source and the material between the source and the detector. So this is the operation scheme or principle. The source is here, the detector is here, and medium material is here, if any medium. This is not necessarily present in the simulation. So, in the beginning, let's emit one alpha from the source and draw lots of the location of the alpha particle emission. For example, in this case, in this place. Then the software calculates energy loss in the source, if the source is thick. If the source is thin, there is no energy loss. Very easy, basically. Then if there is some material, then we calculate alpha particle energy loss in the medium. Of course, we have to know the stopping power. We have to know what is the material. Then we take into account detector response and go back. We can do this 1,000,000 times very quickly. And that's it. It sounds very easy. And it is. So this is coded by using Fortran 90. We have nowadays user-friendly user interface by using Java. And this code has tested in various cases, and we have done many publications which shows that this code is valid. The results are okay. But of course, you have to give correct input information to the code. Most of the data needed for this code, for example, the nuclide library, it's ASCII format, so you can easily change, for example, the nuclide data. Only the main alpha-emitting nuclides are here. I don't remember the number anymore, perhaps 30, 40, 50 nuclides. Okay, how to start simulations? You can start, for example, clicking one of those examples and then just simulate the result, like this. For example, this Thule particle that I showed you, the particle picture is in fact here. Let's open it. Sorry, where is my mouse? What happened? I cannot see it here somehow. Okay, I can see it there.
You are in PowerPoint now. You should go back to.
Oh, sorry.
Yeah.
Yeah. Sorry. Okay, let's open this spectrum that I showed you already. So let's assume that the particle I am analyzing is spherical particle. I know that the particle shape is more like a potato, but let's assume it's a spherical particle and having plutonium-239, americium-241. And this is the number of decays coming out from the particle. So particle diameter 1 micrometer and density close to 9. So what happens? Let's do this is the measured spectrum. Let's do the simulation. What about the size? Is it correct? Is it 1 micrometer in diameter? No. No. Okay. Let's change the diameter. Could it be something else? Any suggestions? 5, okay. Point
1 micrometer.
0.1. Okay, let's do it 0.1. Oh, 0.1. Now you can see that the peak shape are very narrow. So definitely this particle is not very small. I will delete these so that we will be mixed, not mixed. Okay, let's assume that the diameter is how much? 0.5. As I told you, it's sorry, 0.5 is it's this.
How do we know what exactly is our particle size?
We don't know, but we only have a spectrum, and we assume that it's a nuclear fuel particle or nuclear bomb particle. We don't know basically, in this exercise, we don't know the particle size. How to get it out?
Scanning electron microscope?
Of course. But if you don't have scanning electron microscope, which is quite expensive, then you can do it this way. But let's try to do such as, or to estimate the activity. What should I put here?
5.
5.
Still 10.
This is 4. 10, okay? No, sorry. Quite close.
15.
15, all right. Oh, here. Oh, now we have troubles. What's the correct diameter? But please remember that I showed you in one of the slides that, okay, now I know that this is a potato-like particle. But if you don't know that, you can try to estimate so that particle might be ellipsoidal. For example, this case, you can see the X diameter is 27, Y diameter is 16, Z diameter 9. Okay, it's of course in real life. If you don't know the size or shape of the particle, this is a difficult task. But now you can understand what kind of things you can do with this software.
So can I input a file into this?
Yes.
For example, if I have a spectrum,
Yeah.
can I put it?
Yes, you can. If you are measuring this gray spectrum in your systems, you can put it as an input if in this code.
So what should be the format of the file?
Well, you should check it here. There's an input. I think it's this one result. Oh, this so-called PhD file. These are ASCII files, basically.
You have to convert. Or you can put it to ASCII.
All right, let's go back. I will delete this.
So how do I input and ask the software to pick up a file from somewhere? So
By using this way. You can open.
suppose we are inserting some file, and from that peak, can we calculate the particle size?
That is what he was saying.
Yeah.
It's the same thing, yeah.
Yeah.
So using that file, we are adding random numbers,
Yeah.
particle
Which is
size,
okay,
so
which is
matches.
fitting.
Yeah,
Okay,
yeah.
that is the.
Okay, I will remove these things and let's go in the very beginning. Let's assume that I have only this polonium source. Let's select the nuclide
So you know the
P polonium here. Let's select nuclide polonium. Let's assume that it emits. Why this is so?
So is that the decay per second? Or
This is total number of decays. In this case, it's 1 million.
per
So
second or total for
total
counting time.
number of counts.
Counting time. For counting time.
So it depends on the counting time, of course, but this is total number of emissions that this software uses. And now let's assume a homogeneous source with diameter of
10.
10, thickness quite close to 0, and density, it's not relevant here, but let's assume that the density is 1.
Then it's water.
All right, let's see what is the result. You made polonium measurement yesterday. I haven't seen the result, but let's see what's this. Okay, the result. Basically the same is this.
It is similar.
If the number of decays is much smaller, for example, 10,000 alpha emissions, then the spectrum looks like this. However, if the radiochemical processing was bad, so it was not successful, what might happen? It might happen that the source thickness is larger. Now it's practically 0, but in fact it's of course not 0. Let's assume it's well, not 5.
5 is too much.
All right, let's see what happens. I put 2 extra zeros here. Just do the simulation.
Yes.
The result is this red one. I will remove this blue one. Let's assume that the thickness is 15 micrometers. Do you want to have any other thickness?
100.
100. Okay, let's put it there. No.
The thickness.
Yeah. Okay, it's very slow in this case because it has to take into account stopping power in this very thick source. Okay. And this calculation is not very fast. Okay, I can stop it in this calculator and use a smaller number of alpha emissions. But let's see what happens.
We have
So what is the side thickness?
It should appear soon. Let's see. 75, 76. Oh,
So can you remove the other 3 peaks once?
remove.
Yeah, remove the other red and green and black peaks.
Yeah.
No, not that.
Black,
Yes.
red, and green. So, what's the idea of this? Now, if you done something incorrect procedures in your chemical tricks, sorry, I don't understand chemistry, but you can check that, okay, you can find the reason why you missed. This is just an example. But as you can see, it's a very easy way to do things. Of course, what you can do is that let's check a filter, for example.
Why can you put some absorbing layers and show?
Yeah, okay, let's do that. So, sorry, I have to change this because calculation may take too much time. Let's assume that the sample thickness is very thin, so 0.1 micrometers, and let's put absorbing layers. Okay. Oh, now I have to divide the layer. Let's assume that the density is, I think this is the density of air. Is it so?
Yes.
I think so. But sorry, I have to check one thing. The distance was 3 millimeters. Okay. I assume that the thickness is 5 point. Sorry, it's in micrometers. Now it's close to 6. How many? Is it? Yes, because the source to detector distance was assumed here 6 millimeters. I just put 5.9. And let's assume that it's.
So you have to remove 1 9 from that.
Is it so?
Yeah.
How many nines are there?
There are too many 9s. So now it is fine.
No, it's okay.
1 minute. Correct?
And
One more.
layer.
Correct. 6 mm. Correct.
Sorry, I have to check how this is. Let's assume it's composed of hydrogen. I don't want to change it now. Let's do the simulation. So, okay. Let's do first the simulation without this layer. Run simulation. Oh, I will delete the. And now I take absorbing layer into account. What happens? Let's see. I don't know. So, what's this effect? So this is definitely polonium attenuation. All right, I will stop it now and show you some slides. All right, so using this ASIS software, you can usually proceed in this way. At first, you have to determine the detector response, then define the source characteristics, then put some absorbing layers, if any. Neglect these coincidences, it's a difficult thing, and then just do the simulation. Very easy. So you can define detector properties. I mean, full width, half maximum. In this case, it was 14 kiloelectron volts. And then tails in terms of also kiloelectron volts. There is in this picture, there is only fast and slow component. So this is fast and this is low component. Here are only two tails. So you can select source type, homogeneous source here, radioactive particles, or particles in a homogeneous source like a filter. Select a radionuclide, select a number of emissions. Number of emissions. How to start the simulation? Just run. And you can calculate the geometric efficiency very easily in the same way. Just put the geometry date. So you can delete simulated spectra. You can change the axis values here. This is if you want to put this code in your computer, you can try to do these exercises, which are very easy. We don't go through these here. Three types of source types: homogeneous source, particles in a filter. We studied the effect of particle size. So this is an example how particles may penetrate in the filter. So in a homogeneous case, radionuclides are these, and they are more or less homogeneously distributed. In case of filters, most nuclides are quite close to the filter surface. Material composition. I cannot show it just now, but it can be done easily. Effect of particles in a filter. Material between the source and the detector. No absorbing layers or use it. Simple selection. Please do this later if you want. Just add some layer, define the elemental composition and density and thickness of the material. I neglect these coincidences. And there are some additional features. Okay, run geometric efficiencies at small source to detector distance or large distance. Calculation is very easy. So you can save the generated input file. You can open the desired input file if you are saved it. You can look at other relevant information. Okay, I neglect this one. There is online help, of course. So you can select axis types, colors, etc. So you can also copy the selected file into the Excel or into MATLAB if you want. You can change colors, line thickness in this case. So this is only a small introduction, but ASI can be easily used in a variety of different applications, such as emergency preparedness, to generate alpha spectra that may be identical to those obtained in a real measurement case, and training in order to understand the phenomena that has an influence on the alpha spectrum in question, and also in research and technical development. All right, this is it. If you want, we can of course do simulations more. But what's the time? Is it now time for the lunch? Yes, it is.
Any questions? We are going to the lab.
Yeah. All right. Thank you very much.
So after lunch, you can assemble here, and we start at sharp 2 o'clock.
Yeah. Have you
ಅವನೇ ಇಶ್ಯೂ ಅದು ಇದು ಮಾಡಿದ್ರೆ ಆ ಥ್ಯಾಲಿಯಂ ರಿಲೇಟೆಡ್ ಇಶ್ಯೂ ಹಾಂ ಹಾಂ
So he said we have to take about that branching factor.
ಅದೇ ಸೊ ದಟ್ ದೇರ್ ವಾಸ್ ಎನ್ ಇಶ್ಯೂ ವಿತ್ ದ ಥ್ಯಾಲಿಯಂ abundance. So you should use that 33
36 and 45.
yeah 36% you have to take. Okay, and today again we are repeating the same experiment. Batch which has done the experiment with the gamma spectrometry will be going for alpha spectrometry, and the batch which has done alpha spectrometry will go to alpha spectrometry again for 10 minutes, and you will see the spectrum which is acquired. Okay, and then you take the counts, area under the peak, and then you calculate the activity. Maybe that you can do it in the evening, but so you take the counts, note down the counts, and then come to gamma spectrometry. Then yesterday I said this equation for calculating the polonium activity from the tracer method. You can write down polonium 210 activity. So that is in becquerel is equal to 209 active polonium activity becquerel divided by counts under 209 polonium ROI into counts under polonium 210 ROI. Region of interest, polonium 210 activity, counts under polonium ROI into polonium 210 activity. Yes. Okay. This is also becquerel. Now polonium 210 polonium tracer activity we know. So this activity you can take 5 dpm. Okay, or 5.0 divided 60 dps or becquerel into the mass of the tracer. Mass of the tracer, that gives you the total activity in the solution. Right? 5 dps or 5 becquerel. Or 5 by 60 becquerel. So many, this is becquerel. Right?
Should we use the mass in gram or kg?
Huh?
Should we use the mass in gram or kg?
It is up to you. It is up to you. Whether you want to report it in becquerel per gram or becquerel per kg, it is up to you. Okay? Because there are one section of scientists who always sit in the becquerel per kg who work on radioecology. Yes, ma'am? Yes. Those who work in earth science, they report it dpm or becquerel per gram. So it is up to you. So what we do in the lab today is we note down the counts under this. We note down the counts this. And to calculate the polonium 2 activity, you also require mass of the sample. If you want to report it in mass of the sample. Okay. So this mass of the sample Rashmi will give you for the particular sample. Okay. So yesterday we have loaded phosphogypsum sample, and yesterday we kept one for plating deposition. So later, after you finish the gamma spectrometry, if you want, any one of you want, or as a group, you can go there, remove that silver plate. Now it is more than 20, it is almost 24 hours, and by evening it is more than 24 hours. You can remove it, wash it with the alcohol, dry it, and put it to the detector. That spectrum will be available tomorrow. Okay. The batch which has loaded sample yesterday will get the data today. The batch will be which loads sample today will get the data tomorrow. Okay. That is the thing. And tomorrow, if you want to spend time with the sodium iodide, you can do that. And otherwise, what you can do, we can give you reference materials in various geometries, samples in various geometries. You count the sample, you determine the activity. Okay. The target is on Saturday, if I give some sample, you should be able to report the activity of the various radionuclides. That is the target. Okay. So today we are doing gamma spectrometry and alpha spectrometry, and tomorrow and day after tomorrow, it is up to your wish, whichever way you prefer. We give you unknown sample, we give you reference material, you count both of them and evaluate the activity. So that will be the real hands-on. Okay? Right. Any questions? Rashmi ಅವ್ರ ಇದು ಕೊಡ್ಲಿಕ್ಕೆ ಹೇಳಿ. Mass of the sample. For the sample, the yesterday we have loaded. Ask her to give the mass of this tracer. And you take the tracer activity as 5 dpm. Okay? Right. So, hogli ಅವರು. So the batch which has done alpha spectrometry yesterday, go there quickly, get the record the counts. Is it okay, Roy? Yeah. So today you can be there both in alpha spectrometry and gamma spectrometry. Yeah.
এখন আমি তখন এটা বলতে
ಹಾಂ
नेट पावर होना है
बेटा
नेट पावर होना
इज्जत
पावर दार इज्जत
इज्जत
इसको रेंट होना था वे देते ना
लाइट वाली तरह मुझे
no liquid nitrogen now वो आइटम देखते ಹಾಂ ಆಯಿತು ಕೆಲವು ಆಯ್ತಾ ಸರ್ಕ್ಯುಲೇಷನ್ ದಾದ ಬೀಮ್ಸ್ ದಾದ ಬರ್ಕೊಂಡು ಆಯ್ತಾ ವೇವ್ಸ್ ದಾದ ಹೋಗ್ಕೊಂಡು ಆಯ್ತಾ ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಮಾಡ್ತಾರೆ ಈ ಖಾಲಿ ವಾಟರ್ ಇದ್ದಾನೆ ಆಯ್ತಾ ಸರ್ಕ್ಯುಲೇಷನ್ ದಾದ ಬರ್ಕೊಂಡು ಅದು ಬರ್ತಿರ್ತೀವಿ
which university?
I'm from Vietnam.
Ethan.
were working till 9:10 yesterday, right? So today you will be doing that. Okay. Yeah. So what are we going to do today? So today we will be understanding the basics of gamma spectroscopy. So do you remember yesterday's class? I'll be testing that your knowledge from yesterday's class, and I think you should not speak much today. Any experienced people in gamma spectrum? No. I'll separate them. all all the all the participants who have already analyzed gamma spectroscopy stand in one side and okay. So today I will test your knowledge from yesterday, and we will give you some samples. We will analyze some samples, and ultimately we will get some efficiency values. Okay. So we'll, without wasting much time, we'll start the session. So initially, I will be running couple of samples, and you will have to identify the peaks. What are the peaks that are found in gamma spectroscopy? No. In one, for example, I give you lead peak. So in a lead peak, what are the different peaks that is present? Photo peak and Compton peak and backscattering peak and X-ray peak. Okay, X-ray peak we might not be able to get, but rest of the peaks you have. And there is one more peak. There is one more peak. No, think. No. Think. No, a coincidence is okay. Yes, annihilation. So DA people should not speak much. Okay. So this is a sample source, cesium-137, 4 kilobecquerel is the activity, which is not much, as you know, but it will give you a fast counting and will get some spectrum. So if you use a soil sample for this same source, I'll have to keep for 1 day. So initially, let us see what are the peaks that we get from cesium-137. Cesium. It's a point source. Okay. Basically it is for safety. So see, I can handle it safely like this. Yeah, red gloves. Gloves.
Can we
Other
efficiency? No, because otherwise
see,
the other question is like you have done the calibration with respect to that while something like that.
No. The thing is, see, how do I handle this point source? So this is very small. It can be lost, and you know the problems with the lost source. So so for example, people from DAE already know, you might be already knowing, if you lose this source, for example, you have paid something to BAERB and you have procured the source, and somehow, somewhere you have lost it, you have to report it as soon as possible, and they will check once in a while. They will come, I think, once in for 2 years or 1 year, or once in a while, I don't know the time period, they will come and check how many sources that you are already having. So you have, suppose if you miss, you have to report it, and a lost source is a big headache. It's not even enough if you pay them back about the source, or because you don't know where it has been lost, you don't know what are the consequences of it. So you have to be very careful with this source. So what we do, how do we maintain here, is by having a separate locker room for all the sources, and we make an entry on who has taken it, and he has to return it as soon as possible, and if it is missing, he is the one who is responsible for the source. So this is about source handling. So point source can be lost anywhere, but this is easier to find. So that is the only concern. And point sources we don't use for calibration, except for energy calibration. Efficiency calibration by using point sources of no point, correct? So you will understand what we are speaking. We might be speaking Chinese now, but after this class, we might be in the same. Yeah.
There are so many point sources like this, no?
Yeah.
So all these point sources you have kept in separate.
Yes. All the point sources are in separate bottles, and it is labeled. It is labeled, and it has its activity values, the date of. So you can see that sealed gamma source, cesium-137 procurement. What is that? They give an activity and they give it on a date. So this is 4 kilobecquerel on January 2023. Okay, so suppose if I measure today, this may not be 4 kilobecquerel. Cesium has a long half-life, relatively a long half-life. It might be around 3.8 kilobecquerel. But some other sources, let us say cobalt has a half-life of 5 years. So after 2 years, it might be like 3/4 of the original. So we need, yeah. Yeah, there are other sources. Iodine is even less. Iodine is like 8 days. So you need to know, so when you're getting a source, you need to know the activity, on what date the activity is given. And so that is why we have given all these details. So now when you are going to keep a sample inside a gamma spectrometry, detector inside this lead shielding, I've explained all this electronics and these things in the first class. Okay, now what are the care that I should take? So initial care is that, as I mentioned earlier, there should be not even a speck of dust in this sample. Can you tell me the reason? Yes, once if a speck of dust goes inside, it is very difficult to remove. I don't know where the dust is. I can put IP, I can wash it again and again, but I might not even find it. So when you do the MDA calculation, you can see that even one count can give you a higher minimum detectable activity, and that will affect my counting. So what we want as operators of a detector is the lowest detection limits possible. For example, the samples, geological samples, you have very small volume and you will have very low activity. This one, environmental samples are also having very low activity. Then if my MDA is higher than the activity present in that, so I cannot report it. So that is why we should always keep it closed, never open it unnecessarily, and when I'm keeping it in, and I should wash this thoroughly. So now the last batch asked me one question. So you are going to analyze. No, that is acetone. Okay, IP or acetone, something that dries too quickly. So I wash it all the way. So the last batch asked me one question, peculiar question. You are using soil samples. How can you ensure that there is not even a smallest amount of dust in this bottle? How do you ensure that? How do we do that? No. So that is the reason why we are using the slippers in this, so that the dust doesn't come in. The main reason is that we don't do the sample processing and counting in the same lab. So the sample processing lab is separate, and dust samples are not even processed in this building at all, not even in the lab where you went yesterday. So the dust samples, the soil samples are processed in a laboratory outside of this building, where it is sieved and removed all the dust particles, unnecessary items like roots. These all are stones are removed by using 2 mm mesh, and then again sieved by using 450 micrometer mesh number 42 or something, I'm not very sure. Then we seal it, because cesium and all are more attached to the clay particles than to the soil particles. So there is some things like that. So then we seal it, clean it thoroughly over there, and take it to the lab above for for the equilibrium to happen between radon and its daughters. Okay, that is important, that we have already explained. I am not going to explain in detail. If you have doubts, you can ask later. So we seal it and keep it in lab. There also one amount of washing will go through, and from there, when it comes here, it will be already clean as this. Still we clean it and keep it inside, so that 3 or 4 times it is cleaned thoroughly, so the bottle doesn't contain any kind of dust particles. Because once a small amount of dust goes inside, it is very difficult to reduce the MDA. Okay, so this is the basic laboratory cleanliness and laboratory routine that we have to see. Okay, now the high voltage is set. I have explained already in the first class. High voltage is set, amplifier is set. We don't have to do anything afterwards. Now what I have to do is that first thing, calibration. What is the first calibration that we have to do? open that sheet of paper. First calibration that we have to do is energy calibration. So what does this energy calibration mean? I have to check whether my peak is in the right place. For example, if you are using a cesium source, this is a cesium point source. Where should I get my peak? 661.6. What if I get it in 665? It might be some other radionuclide. If I get it in 609, it is bismuth 214. So then even if my sample has cesium, I will identify it as bismuth 214. Do we want it to happen? No. So we have to check whether it is proper. So let us check. So I have used cesium 137. So you can all come closer. Okay. So I think you need to have some space for them. So this is a software, GIAN 2000 software. We have renamed as gamma acquisition and analysis for our use. Okay. And I open, keep a chair in the detector number 2, MCA. Okay. So now this is when I open, I get a window like this. You have already seen this software, right? You know how to open a detector. So can you tell me how to open a detector? File. Okay. You have opened the same software, alpha spectrometry. No.
MCA.
No. Open the data source. Open data source. Yep. And now select detector. Okay. Then you have 2 detectors over here. So this is our detector, detector 01. Okay. So what we have to do? File, open data source. So this is for this this software. You might be using other softwares as well. Okay. So that will have different source. The first thing what we have to ensure is that your detector is what you are seeing here. So detectors controls are there. Okay. Now I am getting detectors control. I get start, expand, clear. All these controls are activated. Correct? Now let us set the time. So how to set the time? Setting time. Yesterday you have done the same experiment.
There we set the time and
How? No?
before display.
Okay, display.
No, MCA.
Yes, okay, MCA and
Acquire setup.
okay, acquire setup. Okay.
And that
You have time.
Yeah.
Okay, so I'll set, since this is an active sample, I'll set it to 100 seconds. Okay, let us see how the peak comes. So I've set, this counting has started. You can see that peak is starting to form up. So I'll just put expand on. So this is the peak that is starting to form. Okay. So you can see the peak over. So this is a zoom window, you already know. So where is the peak? It is exactly at 661.6. So the photo peak is correct. Okay. If not, one channel 661.7 or 661.8 doesn't make big difference. So it is in that peak. So my energy calibration is perfect. So I don't have to worry whether my results, whether the identification of the radionuclide is proper or not. Correct?
So actually, you are placing this point source to identify whether the energy
Yes,
calibration
is
correct
correct.
or
Yeah,
not.
yeah. So if this is not right, what I will do is that I will play with amplifier.
Okay.
I will change the amplifier settings. I will change the gain settings in order to make this fit into the curve. So suppose it is over here. I have super fine gain or fine gain that coarse gain. So to shift this to this location.
Okay.
But once you do this, if your detector amplifiers are all working fine, you need not change it at all. You just have to give the bias voltage.
Okay.
Once you give the bias voltage also matters very much. So bias voltage should not vary. So once you set a bias voltage, the same bias voltage should be there throughout the lifetime of the detector. Or if it changes, you have to change the amplifier settings. So here I am giving a plus 4699 volt, that is 4.6 kilovolt. That is set from the day this detector has come to this lab. So it is not at all changed. Okay. And all the other parameters also need not be changed. It will be like that. So that is why we have put a sticker on the other amplifier. Can you see that? Please don't touch. Can you see that? So that is a manual amplifier. So because we have set that parameters, so even if a small modulation is done on the amplifier, then this thing will not come here. Okay, so this point is clear. Now you have to identify. Can you show me the peaks? Can you show me the peaks? So I'll put an expand over here. Can you show me the peaks? Compton edge. Where is the Compton edge? This is Compton edge, correct? This is Compton edge. Where is your photo peak? Photo peak is here, 661. Where is the other peaks? Annihilation peak. Where is annihilation peak? No, it is not visible here. Okay. 511. There is no annihilation peak because it is short counting time and already the baseline is very much high. So Compton, where is backscattering peak? Backscattering peak is somewhere over here. Can you see? On small, yeah. No, it's 186 somewhat, I think. Okay, somewhere over here you can find your backscatter. There is an X-rays are beyond this, beyond these areas. Okay, so there is one more peak over here. I think this should be also backscattering. So you identified whatever the peaks that are there that we have that was explained. Is there any peaks that is missing that we have discussed and we are not able to find today? What peak is missing? Annihilation peak. Okay, annihilation peak is not visible. Any other peak? X-ray you cannot see. One more peak. Not backscattering peak is somewhere. One more peak. No. Something. Yeah. This one, it is copper coated. So what do I say? The rebound is much less. Okay. So there is one more peak. Think. Which is not present in this sample, but it would be present in some other sample. In this sample, it is not there. In some other sample, it is there. I want you to tell what is that peak. No. Nothing related to that. It is related to the gamma spectrometer itself.
Hair production.
No, that is annihilation. Think. Okay, you think. I'll keep another source and then you find out that peak. Okay? Bremstalling is again X-ray. X-ray is, see, X-ray because we are not going below 30. So, maybe it's a summation peak. Yeah. Why some peak is not present in this sample? There is only one. So if there is two peaks that is produced, then it will add up and you will get a sum. Yes. So let us see. If you are getting that peak here. Okay. So somewhere you have forgotten everything, but somewhere you remember also. Okay. So let us see. So this sample is cobalt 60. So where should I get the peaks? Cobalt 60. 1.1. 1.1 what? MeV. KeV? Okay. So let us check. So I have a peak over here. So this is 1171, correct? 1173, okay? And what is this? 1, okay? Down ಮಾಡ್ಲಿಕ್ಕೆ ಆಗುದಿಲ್ಲ. Chair ಇದು. 1.3, 1332 keV, okay? So we are getting both the peaks. 1.13. Okay.
1.17, 1.13.
Yeah. Yeah, two peaks. And where can you identify the Compton peak? 1.33 and 1.17 MeV. No. Some peak. It is not average peak. It is some peak. So why does some peak come? Because at a certain period of a detector, both the peaks are, just remove this. So at a certain moment of a detector,
Constant peak and some peak are same or different.
coincidence, it's same.
Because we said coincidence peak.
Yeah, some peak. Yeah, coincidence peak, some peak. Yeah. So what happens is that at a certain moment, as sir explained in the last class, yesterday's class, at a certain moment of the detector, let us say the resolution of the signals are produced in nanosecond range, whereas MCA has microsecond range or something like that. So in a second, when you get two peaks of 1171 and 1332, it two adds up. So we get one peak, both the peak addition. That is what it is called as coincidence peak or some peak. So it is over here, 2.505.
So coincidence peak and some peak are so both the same.
Same. It is same, right, sir? Coincidence peak and some peak are same, right?
Coincidence peak.
And some peak. Summation peak. It's
a summation peak.
yeah, it's the same thing. Oh. So I hope this much is clear. So can you identify the Compton edge over here? Where's the Compton edge? Here. Somewhere over here is, yeah, there are like two Compton edges or something like that. And what else do you find? Is there annihilation peak? 511. What is the energy of annihilation peak? It should be there in 511. Why 511? Rest mass of energy of electron is what?
2,511.
Yeah, it's 1 point. It should be it is a pair production peak. It's a pair production. It is half of rest mass energy of an electron. What is the rest mass energy of electron? 1 point. 2 into 5. It is not 511. 1.012 or something like that. Oh, yeah, something like that.
1 mega electron.
So half of the rest mass energy of a electron. So it should come somewhere around 511. So let us check. So here it is not that much visible, but your samples it is definitely visible. You can see in your spectrums that we give later. Okay? So this much is clear.
One more question.
Yes, ma'am.
Here 1.17 and 1.33.
Yes,
Peaks are
yes.
taken forward, both equally probable. 100% probable, right? 100%. Every time abundances, I am talking in terms of.
Yes, it is 100%.
Correct. Then why that, which peak is more? I think the first peak is shown more compared to second peak. If you see the area under the curve also, first peak will be more.
I don't think so. It must be almost similar. It should be almost similar. So yielding will be different. No, yield is same. No, yield is same. Yeah, it will not be similar. Sir. Yes, correct. Efficiency is less. Yes, sir. Efficiency is less. Efficiency decreases as the energy increases. So counts will not be same. Yeah. I'm sorry. Thank you, sir, for saving me. I would have. Okay. So shall I remove the spectrum? Yeah. Okay. So we will start. I will show you a sample spectrum developing of a uranium sample. Okay. But you will see how long it takes for a uranium sample, like the uranium RGU. Yes. Okay. So this is RGU. So this is what we call it as RG stands for 1 minute. Reference material uranium. Okay. So reference I'm not very sure. It's actually IAEA reference material RGU, and it has a code name of RGU1 and RGTH1. I think so. Can you take that file over there? Yeah, I'll show you the exact. It's in the first drawer. There is a file. Yeah. Yeah, you can get it in Google. Okay. So I'll keep this inside and I'll then show. Yeah, this is uranium. Okay.
completely built.
No. You can see that there is some gap because this was first made in the year. I'll keep it inside and I'll then explain. You can see that there is some gap. Okay, I'll explain the reason for that gap. It is not advisable to have this gap as per our last thing, but you also forgot me to tell me something. I've not cleaned this sample. Give me that ice. Actually, I had cleaned it yesterday, so it does not require cleaning again. But it's best to have a standard operating procedure that you clean it every time. You assume everything is dirty. So, okay. So I have a dustbin over here. So I'll just throw it. So I have cleaned it. You can see. So I just homogenize the sample. No. Yeah, I think this is fine.
It should be plain.
Yeah, it should be as plain. Yeah, it should be. It should be homogenized. So if you fill it to the brim, you don't have to worry about homogeneity because it will not move much.
See, actually you are keeping to this much level.
No, I filled the sample and to the brim. But I'll tell you the reason why I could not fill this to the brim. So this sample was produced in the year 1960s. Okay, this sample you don't get now. For example, I'll take you the reference material sheet. So people asked me how, last class also they have asked me, like how do you do it for different samples? For example, if you have sand, for different densities, because we have this much standard materials. So each one is different. So we have so many pages, and in one sheet we have separate 3 or 4 files. So we might have like 10, 15 or many more. I have not counted. So I have reference material for different geometries of different samples. You bring me vegetable, I have vegetable standard. You bring me, I think even milk powder, we have a standard, but it is not radionuclide, I guess. We have standards for elements, elemental standards. We have standards for soil, sediment, water, filter paper, sea plant ash, and clove, spinach. So many things it is there. So you can see that this is the IAEA RGU1 uranium ore. So this release date is 1987. So this is not available now. So I tried to order it, I did not get. So the activity of the sample is 4940 becquerel per kg as of 1/1/1987. But what is the half-life of uranium-238? 4.5 billion years. That is how I understood the age of the universe. Yeah, it is not 1,600 years. I could even hear 12 years somewhere. Okay, so let us see the spectrum. Yeah, uranium is the presence of the uranium. The daughters of the uranium confirm that at least Earth is 4.5 billion years old. That is the main reason to say that Earth is 4.5 billion years old. Okay, because so much of its daughters are present. So I don't know the exact scientific meaning, but the presence of uranium daughters is how we say that Earth is 4.5 billion years old. Okay, so you can see that for 100 seconds, you basically don't see any spectrum. Right? Do you see anything? No, it's almost 50-60 seconds. And you might get some 1 or 2 peaks here, but can you analyze anything? It's all baseline. Can you see this? Can you see this? What I'm trying to say. So see, I have 1 peak over here. This is 609. Okay, but that I can analyze. But what about the rest? So this is 351. There is 1 peak. Okay, I agree. 295. Okay. But nothing else. Some peaks are there, but it is pretty much smaller. So what we do to get good peaks, we increase the counting time. So basically we keep it around 30,000 seconds for soil samples in HPGs in sodium iodide it is around 10,000 seconds. So if still the resolution is not good, if the peak is not coming, if your sample weight is less, so what should I do? I should again increase it. So I can go for 60,000, 82,000, 85,000, 1,50,000. So I have done, so till what level should you do? That's another question. So how to find out the upper limit? So what I do is that if in a soil sample, if I don't find any radionuclides up to 82,000, then I'll say that it is below the minimum detectable levels. Okay. If in vegetable samples, I will go as much.
That time, what will be the weight of the sample?
That is depending upon how much sample you have taken. So it is your sample. How much sample you have given, that is. So sometimes if the sample size is very small, for example, you could not get enough samples. In that time, we should say that it is below the minimum detectable activity for so much counting time for so much grams of sample. So that information is important. What counting time, what amount of weight. Okay. So basically this is it. So now I hope till here everything is clear. Any doubts? Any doubts till here? No. So now I will open uranium spectrum. So we have 3 HPGs, 3 high purity germanium detectors. So in 3 germanium detectors also I will open a uranium sample and give it to you for you to analyze. Okay. You will individually have to mark, I will show you how to mark a region of interest in one sample. Basically you have to mark region of interest for the samples that are listed. Do you have the list?
Yeah.
Okay. So you have the list, right? So you have to calculate the region of interest, area under curve, and all those necessary details. And then I will give you the activity of the sample, and then we can calculate the efficiency. So is this much clear? Any doubts till now? No. Yeah, that we will have to take 36. That is because I will tell you how. Why? Okay. It is because of the branching factor. So if you don't consider the branching factor, and if you take 99, your graph will not come up. That you will understand in the end. Okay.
Compton
Yeah.
at what electron, what energy?
That you can see.
You can
No. Compton peak is corrected in this. Yeah. One more thing is that in any gamma spectrometry, it's just them, right? Yeah. So in any gamma spectrometric analysis, you usually get a Compton peak or Compton addition of Compton. What do we say? Not Compton correction. We do it later, but there is some contribution of Compton. So what is that thing? So if I have to explain it in an easier way, it's something like these peaks which are on the end, which are on the last, higher energy, in the last in the sense towards the higher energy, those contribute some Compton energy, some Compton peaks to the peaks that are behind them. For example, the last peak in thorium series that we analyze is thallium 208 at 2614. Okay, which is abundant, which I have taken. Now that 2614 peak will contribute something, some Compton active counts to the peaks behind it, which is bismuth 214 at 191764. K40 1460, and this bismuth 214 at 1764 will again contribute to K40. So that is why you're getting graphs if you had seen this graphs properly, you could get like the baseline decreases. Yes, at the end baseline becomes 0. Initially it will be also higher and higher because of these Compton contributions. So you have to correct it for it. Okay, so there are Compton correction formulas. Some of you have used it, but this system gives you the result corrected for these Compton corrections. Yeah. Okay.
That's really easier.
Oh, okay, but we use this spectrum. It's okay, sir. Once I finish it, we can show it then.
Not like that. You can depth there this one so that the entire curve and that one.
Oh, okay. I think display it is somewhere in display preferences. Yeah, so I can just background spectrum background is
RGB change.
Wait. Okay.
All is up.
Okay, white and
This one.
reference spectrum blue,
Okay. Blue, take this one, this
and just gives blue. Okay.
fill.
Yeah, but I prefer the other way around. So the other way around is much easier for me because I can see individual counts. So this is another way to look at your spectrum, but I think ORTEC gives similar results, right? But you can see the peaks, but individual counts is better in the other round. So we can set it any way we want. Yeah? Yeah. Wait a minute.
instead of
No. I think. No. I'll have to reset it. So spectrum background I'll have to make black, and reference spectrum. What was reference spectrum? White? No.
It was yellow.
It was yellow, right? Okay, fill, normal. Okay. No. Wait. Background was black, and reference spectrum was yellow. It should do this. Yes. So yeah. Now where were we? I explained about Compton correction. So this spectrum, this software does the Compton correction for you. For example, now I will show you how to set an ROI, region of interest. Then you will understand the Compton correction file. So initially I have set some region of interest. I am clearing it all. So now the first peak, what is the first energy that you have to analyze? It is
K40.
Look at the energy, which is the first energy.
First energy wise it is
46.5.
46.5.
Okay, so 46.5 is somewhere over here, correct? So this peak is not perfect, correct? This peak has been not counted for enough times for the spectrum to be developed. So, but again I'll try to put an ROI over here, so or else I'll open a better peak. Okay, file, I'll go for Genie 2K cam files 138. Okay, it's there in 2024. I compare. So RGU. So I've also given you the weight of the sample, 138.8265 gram, which you'll have to consider while doing the calculation later. And this is the counting time. So now please pay attention over here. So weight 138.8265. 138 gram basically, that's enough. Okay. So this is your you can see here you have channel number, counts and preset time. So you know which time to take. Better to not confuse by here I have stopped the counting at 26,968 seconds. So you can actually take this one, live time over here, 26,968 seconds. Okay. No, you have to take it on your own later, not mark it now. Okay. So now I will remove all the ROIs over here, and then so you can see the peak properly, right? So you know how the peak is developed. It is put into different channels, right? So each channel, so you can see this channel has 988 counts, and it goes higher, gets to the peak and then drops, correct? So you want to put two markers. You have already seen how to mark, right? So here I have to check I'll make as big as possible, and then I'll check the bottommost part. So I have to put the point where the peak is just getting ended and the next peak starts. So this is okay, and here I can see that I can put it over here, and then I'll go display ROI, add ROI. So this is how we do one ROI. Okay, now here you get two. If you can see, there is integral area. So basically there is 67,896 counts of this peak, integral counts. But the Compton corrected count is 36,987. So you have to only take this value, 36,980. So it corrects your sample for Compton effects. Okay. Integral counts is Compton corrected counts. Okay. No, integral is gross counts. The area is Compton corrected counts. So when I made a mistake, everyone jumped on it. Okay. So 4 of you can sit here, analyze this peak. 4 of you can sit in another one. 4 of you can sit in another one. So we will start this exercise. Okay. So now it's up to you.
Why the sample is not up to the grip?
Because I did not have enough samples. So they gave us, I think it was 500 grams of sample. We have 3-4 geometries. Okay, then this was the end last some sample. So I could only get the 138 grams. Yeah. So you can take chairs, as many chairs. One chair is over there. You can take that. Yeah. Yeah, one is this. No, sit, sir.
This could be taken, huh?
Yeah. I will just open it. Illa. I don't.
Take your honorable seat. Come.
1 minute. I'll just open the peak and give it to you. ವೈಶಕ್ಕೊಮ್ಮೆ ಯುರೇನಿಯಂ ಥೋರಿಯಂ ಮತ್ತು ಇದೆಲ್ಲ ಉಂಟಲ್ಲ ಇದು ಮುಗ್ದ ಮೇಲೆ ಕೌಂಟಿಂಗಿಗೆ ಇಡಬೇಕಾಯ್ತಾ
The gamma lens use. This is the gamma lens for 46.
Yes, so I have it in here. Okay, 2024 GIAN RGU. Yes, this is all yours.
Display ROI.
Display ROI and expand will give you this zoom in area. Yeah, I have cleared ROI, display ROI, clear all. Yes. Okay, now you set up the ROIs. You can zoom in, zoom out. Okay. Yeah. So yeah. 1 minute. Display. ಇದು ಬೇಡ, ಇದು ತುಂಬ ಹಳೆತ್ತು. So no, it is 238 gram. So we'll use 138 gram because everyone is using 138, or else efficiency would be confusing. So I'll take 138 gram. No. Wait a minute. 1 minute. Open file location. 142. Okay. Okay. 6 August. No. Date created 22.
Come here.
It's not a race. Okay, display ROI, clear all. Okay, now you do. 1 minute. Background counts will take later. It's not 0. Keep one chair here so that nobody goes near this detector. Okay. So, and you can take one chair. I think you can you bring some chairs from that? Okay. There is one chair over there.
Sir.
There is one point that should be taken into account in the
Often. Explanation work doubt board at the end part record pura stream on the mute one put board
charge full illalo ive charge off
off on the book. Okay.
Because what may happen is that I will show only this one. The point is that actinium emits X-rays too.
Okay.
Their energies are these two.
89 and 92, 93 years.
Around, yeah. But the point is that in some cases, if this peak is big, what happens?
9/11 peak.
Yeah, it happens so that these gammas and these X-rays are in coincidence.
Okay.
What means that if you calculate the sum of 911 plus these two, coincidence peaks goes just here. and here. So, what does it mean? If you calculate uranium activity on the basis of this 1001 peak, it's incorrect.
Yes, yes.
Now you can see here. So, ratio of the intensities of these two coincidence peaks is 0.61.
Okay.
So, if you multiply this peak area here to this 0.61 and diminish this number for this peak area, then you get the correct number. So,
Okay.
point here is that because this protactinium peak is usually very, very small, and then you report something. If you do not check
9/11.
yeah, and especially if you find this 1004 peak, then you have to take it into account, which may in some cases have a notable effect. Even that it might happen that you report the presence of uranium and there is non-uranium.
Did you publish this?
No.
It should. You should.
Well, I think that if you want to publish, I can advise this.
No, I don't know any details of this. You can publish. It's nice. It's very important information to be known.
Because this is a decay scheme of actinium. It is really complex. And I found this phenomenon.
I think I should switch it off.
Around 1 month ago. It was some kind of some sample from one of my colleagues If you look at the data very carefully, so if it is from Vara, for example, then you can find that there is a one
Not the lifetime first. Lifetime same only.
Okay.
Area. 1.11. This is the area. 6.9.
maybe on one day you can.
Before that, please check 583 on
Yes. You might have. If it is written, then it's we can. But it might be intrinsic property. Your detector showed that the bismuth is X-ray. Maybe that one.
Actually, it will come for thorium sample. Since thorium is not there, don't worry about this. Okay, just go for bismuth 609 and 7. You will not be considering here. Yes, but you will not be
Yes, here. 5 to 1 committee. No, you can speak as long as you want. Happy to listen.
No, you will not So you get A40 chances there because
Go back. And your other question.
ಇದನ್ನ ಅಮೂಲ್ ಇಟ್ಬಿಟ್ಟು ಸರಿ ಆಗ್ಬಿಟ್ಟು
Because now otherwise, or when you go, you can
1764.
Thorium will give a separate thallium lead 212, actinium 228, all will come in on the water.
Probably they have
Thorium, so it will not be visible in thorium. Yeah, mine is very small. No, we will not take this. Because it is considered. We will use some other sample for that. In this it is not.
Some traces will be now this is done. Uranium series is done. Okay.
thorium decays to radium 228, actinium 228, then radium 224, and then radon 220. Thallium 208 is soil matrix. We have kept it for 30 days. Uranium is 30 equilibrium. So thallium and thorium are in equilibrium.
To identify what peak is there.
Thorium 232 doesn't have good gamma peak, which can be measured directly. Assuming there is equilibrium. That is important. That is important. The important concept is we assume that. That's why you see the sample for 30 years. Radium is talking to project. You should ensure. That's what Dr. Roy was telling. They will vacuum seal the sample. Why? Because you equilibrium.
See the 587 it is. Not
Roy, you can use this chair.
So what happens is
That's very small value. Okay. Then 661 nothing.
try to check that is separate.
I got it 61.
Up to ನೀವು ನಾಳೆ ಮಾಡಿದ್ರೆ ನಾನು ಅವರು ಕೆಲವು ವರ್ಗದಲ್ಲಿ ಅವರು ಕ್ವಶನ್ಸ್ ಇಟ್ಟಿದ್ದಾರೆ ವೈ
Shall I give you two? Yeah, that we'll have to check. That is a uranium series peak.
65
This one has so many peaks. So it has like 609 is there, 665 is there, 795 is there. Then you have 1120 is there, 1764 is there. So many. Yeah. It's 238, 238, 238. Yeah. But if I'm not taking 238, maybe you do 2 this one, whatever.
Okay, I am not considering that peak at all. Can you tell me the reason why I did not give you that energy, although sir has given?
This peak.
Yeah, PB212. Look at the PB212 peak, like it is 238. Vaishak, can you confirm PB2, let 212? Is it 238? I think it is 238. Yeah, 238.
So we don't have to see this peak.
No. You have to see and tell me why I did not recommend that peak for you.
238.
Yeah. Why? Can you see, sir? Find out.
Maybe that I should that energy some other I should have
Check. It's there in the spectrum. Yeah, there is one more peak nearby. So that contribution can come to lead 212. So then our counting might be different. So we already have thallium-208 and bismuth 214. Sorry, thallium-208 and actinium 228. So why should I go for this difficult peak? So that is the logic. So whatever is a good resolved peak with high abundance, those peak is what we are taking. Bismuth has so many peaks. 609 is there. 1171 is there, 1768 is there, 695 is there, 794 is there. So and many other are there. So which one should I take? So if someone asks that question, which is having higher abundance and which is having proper resolution, like there is like 2 peak separation should be there. It should not be some other peak should not come and join with us. So those things we take care of. Yeah. Background I'll give. Did you do all this?
Yeah. Except K40 and
Cesium 1000. Okay.
These are not
series. Okay.
2614.
Done.
He will give you. Sir will give you that
2614.
K40 and
Take it.
Cesium 1000.
Control left.
No, that is wrong. That is wrong. It is not. That is not the correct way to do your RA. So you have to do this. You have to do this and bring it over here. And now see. Now you can properly attach the lower marker. Or else you can no, or else you are putting it in the half of the spectrum. See, your point was over here. Got it? So if I see from here, it looks that this is the end. but look at now, it is up. So this is the proper way to put the ROI. Okay? So you change all the things. So show me the way you are putting ROI. No, 1 minute. I'll show you. Just tell me whether you're doing.
This peak.
Yeah, if you're doing that way, you should do like this.
Oh.
And
Now
you
how you
should
did that? This
see this left marker is there. This one is either you reduce the size, okay,
Okay.
and enlarge it to an extent where you get something like this. Okay. Now I mark this and put Control L. So this marker has come. So this marker is over here. Now you get, see, if you put, for example, if you don't do this, let us say you have like this, no? Look at this peak, looks something like this. This is the end of the peak, this is the end of the peak. So your answer is wrong. So you have to see, now when I do, see, it is actually underestimating 2-3 counts. So I have to consider that.
This should be the starting and
This should be the ending. Yeah. This should be the ending. Just where it drops. Okay. So this would be the starting, and somewhere this can also be the ending. This also can be the ending. Okay. Yeah. Ma'am, can you show how you did the ROI? 1 minute. I think there was some mistake. Not my side. I'm not saying that mistake, but you might have made a small mistake while taking ROI. So what many people did was, I don't know whether you did the same thing, but please confirm. Okay, so this is the data source.
Okay.
I'll see where is your ROI. This one? This is your ROI?
Yes, sir.
Okay. No, this one is okay. Let me check. Only one ROI.
Yeah, we cleared.
You should not clear. You have to save it for the background. You should not clear it.
Okay, fine.
Okay.
Four more.
Okay. You will do it. Okay, you do it. Now I'll tell you how to properly. Our hತ್ರ ಹೇಳಿ clear ಮಾಡಬೇಡಿ ROI ಇದು. Okay. So now I'll show you. So you take this peak. So now supposing you put ROI from here. So this looks your left marker, correct? And this looks your right marker, correct? Control plus R. But now when you zoom out, okay. Okay, 1 minute. Okay. See, now you have underestimated 2-3 counts. So it should have been like this. So you have to zoom out as much as possible, or you have to make it as smaller as possible, and then take the ROI. Or, if you don't do that, what will happen is that it will be somewhere over here, and this marker will be somewhere over here. So look at it. Now you look at the peak. See, it looks from here, it looks fine, but it actually should be over here. Okay. So that thing.
We have cleared now,
So you started.
from
Yeah.
the
Beginning you do that.
Check first week we checked it. 295.
Will it make that?
Whether it is 295.
It will. Because see, from here to here, now do more. This is not enough. See, that is what I'm trying to say. See, it is on almost over here. It is log 100 m. Okay, so you have to do smaller and smaller.
46.5 in that.
Smaller and smaller as possible. Now you make the marking. So don't make when it is like, the peak should look very clearly for you. See, now I can say that this is my lower marker, this is the lower marker over here. Yeah, or else I cannot do that. Okay, so make sure that you do that correction and keep the ROI. Don't delete the ROIs. And after you finish, you let me know. I'll say how to save the ROI. Okay. And don't delete the ROIs. Okay. Yeah.
Yes, we just expanded. Then you have to get more. 261 where?
ಕೂಡ ಅದೇ
Oh. What is it?
Next.
ये जीनी मूल्य भाई मोटा मूल्य मूल्य
46.8.
अब दे पर दाय कड़े पातेर ना पूरे गेंड राइट पूरे ये
लाइव ना ताऊ
Plot the graph and expand.
We will keep the same value, background will.
One point here and there.
Because you calculate to the decimal place, right? So then,
So you have to take again.
you have to note down the new value.
That should 36551.
This is also wrong.
36551. Okay.
It should be down. But you're marking it. You're marking, change the markings, and then I show you the background.
We found out that the ROI deleted of the hyperline, so we have to reset it. And then in case the ROI was also. This one.
Statistically not as low.
Without the chamber, calling me. I asked you to
Got it. Yeah. Okay. So now we have to store your ROI. Okay. Go for display ROI. Sorry. Display ROI. Store. Store it in GIAN 2024. Your name. Mitra, and what is your name? Okay. Mitra at all. Sorry. So you save it. Same you do it for uranium. Okay. Then I'll show you, give you a pattern.
What do you do? Try zooming out something, make it smaller.
Change the cursor.
I mean, make that box slightly bigger.
How about you are going to uranium and uranium obviously? See?
There is. The background the same ROI we have taken.
There is 19.
The same sample we are getting uranium and uranium. Not the same sample. Different samples. Different samples.
You can get uranium.
It's not 19.
Yes, ma'am.
A14.
It's not 9.
Store what you
So the last bit at least we will save it.
I think you done with all this.
Background.
Then we add ROIs for both. So we
click
can Only thing is here is that the ROI is that's it.
You check that first.
1076.
We have to memorize the
Okay. Ma'am, any concept the right side only elevation.
You can adjust it, like if it is not in that way. Done with the board. You can take for background. Did you see the ROI?
No.
That area you have to
About
40. No background.
I have to type name something. This is for touring.
No background.
Usually these kind of problems is other system won't find efficiency is very
Next 1764. There already, right? Already that you have to check that number very
otherwise like it will be difficult to like this background. Otherwise you have to search in background. Where is my background is everything. Hold your teeth.
how much is it? It's already selected means already
No, it is not showing. It is 20 mark 5.
Why you have to, because cursor now she has already area was selected. Once the cursor is moved,
But again, you have to cut there
set.
No.
Before cursor move, now she is not showing the value of her cursor. Previous. It is a previous value. So
next one is
no, after that cursor was somewhere. It is not that.
how much it is?
No, that's not that. What is that? Before you move, now once you reach, it will not be a cursor was somewhere. That
That is different option.
now you move the cursor. But this value, if you this ROI was already selected. Once you change this, you are again supposed to click display and change this how to re-edit the ROI. Reset the ROI. Suppose I have set this and added the ROI. Okay. Now this will be highlighted. I want to move. Yeah.
So that is 43
How to select this ROI?
Just no.
Plus or minus.
609. So now I do this one properly. Add another. Okay, now let us play with one line. The next.
What is your correction?
61.
Yeah, we break for tea for 5 minutes.
Adjust.
Tea is getting cold. Have tea and come back.
Back when you take it.
So beautiful. For that energy, that is very elegant. It can be zero. Background is nothing but without the source. What a beautiful statement. Wow.
Now making that plus and minus to move from one to the other.
What energy? See, it's just because it's only for brilliant people. Only those people like it. I have a basic package. So the basic package is GIAN course. So any additional information you will have to pay. Your basically from the heading, right? So you will have to pay. Yeah, you pay some people. So you have to pay. Euro is also. Maybe 50,000 euros will be enough. Okay, this Okay, now you have tea. Come, you have tea. Come back, I'll give you back. You can leave for tea. 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 Break for tea. I'll give you the backgrounds later. Yeah. I hope I can be a I don't know. For higher energy use, you might have it gives you the compensation. Please wait for tea. We can meet you later. Or else I'll shut down the systems. Stay a little bit. Or background thing.
No, I am changing the resource and going to the project and seeing the background is very hard.
Keep it as it is. Go for tea. Come back. I'll answer your doubts.
I don't drink tea.
Just go out and come.
Just for her, secret task to delete everything.
Yes, yes.
That we have already.
Hey, Vaishak, what is your name? Just go have tea and come back. It will get cold.
10 minutes.
You want to go directly home.
But sometimes what happens but this is very needed.
What was your zero?
I'll tell you. All after T. Every answer is after T. Yes. Now ask your query. Fast. Okay. Why is your surname sounds like a Bengali?
This is not my surname, this is my father's name.
Oh, when I was in Aitika, right?
Everyone asks the same question.
And then everyone says,
Geology or geography?
Geology.
We don't have that.
yeah, I know, but I know
Then the science
Geology.
just now one Bengali
Science
is
is
yesterday, but Bengali
my
came and asked
combination
whether
of
they
science
got
and
the
information
information
February.
The stall is there, Roma. That time you came, sir, for the food stall.
I think so that time, but we didn't visit, time was not there, so it was just 3 days or 2 days.
Okay. Sir, you.
on the spectral plane, you line spectrum. You will get the net count. So you will know that and for granted is 0 percent.
Zero ಅಲ್ಲ ಅಂದ್ರೆ high count ಇಲ್ಲಿ ಮತ್ತೆ
1 or 2
I think 20 counts something. ಹೌದು here up and down here also you play here click on here zoom out and zoom
Now we have to close the because they have taken the data from the letter, but right now I think they did
4750.
So got the background?
We are waiting time.
We are taking foreign values.
Okay.
50,000 seconds.
the subjects we take from other
Okay. It's up to you. It's up to you. But just give me the graph. If the graph is not correct, the background, who opened this? Maisha?
Yes, no.
Then we have to subtract these.
She is not finder now.
Are you adding the peak or no, you should add. Fix it, no? She already fixed it. First thing she fixed it. Maybe not suppose you should add. Yeah, now she will improve. Second year she is subject. Then she will add. Next year. You could go for it. Yeah, it's
What is the
Take this back now.
60%. How do you take a strategy? Which number you are taking? 61.
I see. How is it? I think that is not this. We'll go to 9%.
We already only samples we might
Same level.
Actually, but they have come to that may be corresponding to something else, right?
that is maybe corresponding to last time I said this might be so it's a uranium daughters sometimes going speak also otherwise you mark because
No, but sometimes
this one has a lot of things.
Is
I think it will be.
your badge, some kind of correction software does. Okay. So this
Our value
P, if it is something
what is
this,
4.25
actually you know the peak should not be like this. The peak should always be in the same line. So now when you do it in the same line, you see that area under the curve is 6.
again I'm right.
So when you are taking any peak, the baseline should be same. You cannot take one baseline over here and one over here. That will the software will make a lot of.
No, but when we took that ROI in the first
Yeah, in that it will be perfect.
No, but then also we took the ending and the ending part.
Yeah, but then both are in the same baseline. No? Almost the same. Yeah,
But
little
some
bit.
confusion will be there.
See, this is wrong. This is wrong. I told you.
8707.
Yeah, I told you to take it from here to here. Okay, this is okay. This is a small elevation, but see, you have underestimated this much points. So that means your efficiency is wrong. Efficiency will be
1461 is
not correct.
So that was
If you do that.
We started doing like this from thorium. We didn't do it for uranium.
because they you get separate sources because that's
But this is from polyers and it was
I think this is more
You already have the
maybe for the natural.
Plus or minus.
You know how to change the ROI. This is the ROI. So just change the ROIs. Store it.
Yes, see the 164.
So I give you a background.
Reactor.
And we are helping for that.
Background is none.
No, sir. So we have you completed this. This is okay.
GIAN is the
GIAN 16. ನಾನು ಅವನಿಗೆ ಪ್ರೋಗ್ರಾಮ್ ಕೊಟ್ಟಿದ್ದು 2022 ಫೈಲ್ ನಾಲ್ಕು ವರ್ಷ ಹಳೆ ಬ್ಯಾಕ್ಗ್ರೌಂಡ್ ಕೊಟ್ಟೆ
ಇದೆಲ್ಲ ಚೇಂಜ್ ಮಾಡಿ
ಈಗೆಲ್ಲ 2022 ಫೈಲ್ ಯಾವ ಫೈಲ್ ಉಂಟು somewhat near that How can I enter?
No, we will take it separate. We may give it separate. Pay 40 and
I just check which is this sample.
we haven't saved this.
Okay,
We
I
saved
will
this.
not touch it. I will give you that one. This is
If we haven't saved it, you know, we will nothing with that.
So now you know how to store the background. The ROI.
ROI just file save.
No, no, no.
Then just give file save.
Display
Okay.
ROI store. Go to GIAN 2024. In that, so this is storage file. So just give one of your name, ROI, storage. So give a name. Then what you do? Then go to background, data source background, display ROI file. That you do, you take it. In 1 5 minutes you take it.
We save this file.
Yeah, save it and
Then this is of Victorian CS. Save office. I'll try TM. Save the directory. This is for the now we have to TM. Now you open the background. Now we will open this source.
Actually, I couldn't get a software event.
So in this yes, we are
Once you load it into the background, the ROI will automatically fall in those slots. You save it properly. That is his no. He said you have to save it in a file.
Yes, same. No, same. No,
So
same.
once you open the ROI section,
It can be starting of things promotion.
it has to be there here. It will be listed.
You can make it now.
Hello.
We first
Hello.
send it for I0.